All right, let's now take a look at my favorite Newton's law, the law of gravitational attraction. And for that law, we probably heard this before, that everything attracts everything. That, of course, is not very scientific, but we're trying to say that if you have two objects, for example, here we have M1 and we also have M2, and both of them have a distance to each other. Let's call that distance R. So there's a distance R between the two, and it has been shown actually experimentally that the gravitational attraction between M1 and M2 is really proportional to the product of the two masses and inversely proportional to the square distance r. And we will write this down as a formula in a second. I don't expect you to memorize this just because I say it, but please understand that the attraction between the two masses are really dependent on the amount of the mass, and the more massive they are, the more attracted they are to each other. And they are also inversely proportional to something with the radius here, or the distance, I should say. And that is, the further away they are from each other, the less attracted they are. So that's why in the classroom we always come to the realization that, you know, we should go to the bar next time and find the person that we like and tell them, hey, do you know that you are attracted to me? Because everything is attracted to everything, right? And if you don't believe me, just come closer, you will be more attracted to me. And this can be expressed in a formula. You can say that there's a gravitational force between the two masses, and you know that you found the right person when you can talk about formulas, right? So maybe you can even extend that conversation there. But the formula that you want to talk about is M1 is multiplied by M2, and that then is divided by the squared distance, and we need to add one more thing, which is the gravitational constant. So what we have is the two masses and divide them by the distance. And this is very important for structural applications, because that is how forces are created really here on Earth and actually everywhere, but we have a specific value to them when we deal with them here on Earth. In fact, so understand that M1 is the mass of the first object, mass of the second object, distance between them, and the gravitational constant. And I will not ask you to remember this, but we will use this number in a second. So I will just tell you that this here is 6.673 times 10 to the minus 3, and the unit for that is meter cubed divided by kilogram times second square. Again, you do not need to remember this. Maybe you remember this from your physics class, but it's just a number we need to make this all work here. In fact, I want to talk about how to make this work for the gravitational pull here on Earth, right? So if you, for example, bring the two objects so close together, so consider this being Raphael and this being Earth, then you have a radius here, right, of the Earth, and that radius then would be, let's say, equal to 6.37 times 10 to the power of 6 meters, that is. And so the mass here, m Earth, would be equal to 6 times 10 to the 24, and this is in kilograms. And so then you can actually replace some of the parts if you now consider this piece a structure and you put it actually directly on the surface of the Earth, because then your formula effectively turns into F is equal to M1, which is the Earth in that case, times uppercase G, and then you divide that by r squared. And of course, these are the values for Earth. So this is everything that happens on the planet here, but you still would have to multiply it later on by m2. But think about the values that you're using here, right? So here you would use the 6.673. For r, you would use 6.37 times 10 to the power of 6 meters. And then for m, you would use 6 times 10 to the 24. And that is in kilograms. And I invite you to calculate that, and hopefully you find the number that already pops to your mind. But you should calculate this value. I'm not going to do that for you here right now, but I expect you that you know that. What is this value? I want to know that from you if you use all these constants that I already provided for you here. And then once you found that value, you understand how we calculate forces that really act on structures. And if you really understand the concept of this attraction, then we can actually enlighten you on one more concept that you probably heard before, but my experience in the classroom is that everybody knows that we say, hey, if you have Earth here, right? And we have the moon here, we know that the moon affects the tide on Earth, right? Like how our water behaves in our oceans. The question is why, and the answer is Newton's gravitational attraction. So how does that work? Well, we have water on one side of the Earth, if you will, and we also have water on the other side of the Earth, right? And there's obviously mass to this water, and there's mass to this water. Then we also have mass to the moon. So we have mass here, but what's more important to understand is that we have different distances between the individual water bodies, if you will. So we have this distance here. So let's call that R1. And then we have here R2. And of course, this radius, sorry, I say radius because of the R here, but really the distance here is much shorter than the distance to this water, and therefore this water has much higher attraction to the moon than the water on this side. In reality, of course, there's more complex systems at play, but this really explains what happens and why our tides are affected by that. And I think in your homework you have a fun exercise to think about what happens at new moon and what happens in other times of solar constellation. But I'll let you work that out. Last but not least, I want to leave you with these images here, and I want you to think deeply about the difference between this scale and this scale. They're both called scales. This is actually more precisely called a balance, and this is a scale here. But there are differences to these, and I want you to think about, so think about the differences of these two scales or balances, or however you want to call them. Again, this is a balance or like a beam balance, and this is a scale here. But they have different mechanisms that make them work. So they have working principles. And I want you to really understand why they work differently and when would they actually give you the same results and when would they give you different results. So when would the measurement be equal and when would they differ? So what I'm really asking you here is, hey, where would you have to place these to read the same measurement? or where would you place them to read a different measurement? And I wish you good luck with that, but I think you can answer this based on everything we have talked about on this page and the previous pages. So that concludes our lecture for today, and we can now move on to the concluding page and our checkpoints.